I think we'll get started. I know that the keynote was running late, so there's probably people still trickling in, but we'll get going. My name is Tony Petrosian. I work at Microsoft. I'm part of the SQL Server engineering team. I'll have to stand here. All right. We're responsible for building SQL Server and all of the SQL-related software and services. We're about 600-700 people in engineering, and I'm a group program manager, so my responsibility is the next version of SQL Server, what it's going to look like, and basically delivering that from engineering. Tony Petrosian is my Twitter thing. If you want to send stuff, there's apparently a lot of Tony Petrosians, and a lot of them are very famous. I'm not the famous one. I'm the Microsoft Tony Petrosian. I only say things about SQL Server when I do. All right, so since I'm from engineering, I have to talk about engineering a little bit. And I think it's useful to know how we actually build SQL Server these days. Because the process has really changed since the old days when we used to ship every 5, 6, 7 years. And now the cadence is very different. And we've gone to this, what we call a cloud-first approach for actually building SQL Server. And as you may or may not know, we have Azure services for SQL. So there's Azure SQL Database, and there's Azure SQL Data Warehouse. And those services are operated by Microsoft. And we don't have an operations team, and we don't have an IT team. So the engineers who build SQL Server are also the ones who deploy and run and maintain the services for SQL. So we're on call. If something happens to the service, we're the one who get to go and fix it. And because we run SQL Server services in Azure, we have millions of databases. We have 30-some data centers around the globe. And we have lots of customers using it. We've learned a lot more about how you run SQL Server compared to the old days. Because in the old days, the engineers who built SQL Server they were all good software engineers. They weren't very good DBAs. They weren't really good at operating databases. They're good at building database technologies. And that has changed a lot because when something goes wrong, we're the ones who get called. So we're the ones who automate everything. We're the ones who run the service. And the way we go about building features now is, we have a single source base for all SQL things. So SQL Server, SQL DW, Azure SQL Database. And when we want to build a feature for SQL, we go write the code. It's a single source base. We test it, and we deploy it into the cloud. And we have the ability to do very targeted deployments into the cloud. So we'll take a set of subscription for a set of customers who are interested in trying a new feature under a private preview, and we will enable the feature for them. So only those customers who are interested in the preview will actually see the feature. So as an example, in 2016, SQL Server 2016, we introduced a row-level security feature. But the way we built the row-level security feature is we first talked to the developers. So how long will it take to build row-level security? They said 4 months. So it took about 4 months to write the code, do the testing, and then we actually deployed it into Azure SQL Database. And we had a set of customers in Houston, oil companies, that wanted to use this feature. So we enabled their Azure subscriptions so they could have access to the feature. And they tested it. They wrote some code against it. They told us what was good and what was bad, what was missing. And we iterated on this a couple of times. And in about 8 months, we got to a point where we were feeling comfortable about releasing the row-level security to all Azure SQL DB customers as a preview. And then after a couple of months, we got more feedback. We made some changes. And then we fixed stuff, and we deployed it for generally available. That piece of code ended up running in Azure SQL Database as a GA feature of Azure SQL Database. And several months later, when we shipped SQL Server 2016, that feature was already in there. Because again, it's the same source base and it's the same engine. And our customers in Houston who were interested in that feature, they were just waiting for SQL 16 to ship so they could use it. Because they weren't really interested in using the cloud, but they used the cloud to build their app, test it, and interact with us and give us feedback. And that's how we build features for SQL Server. So most of the features in SQL Server 2016 were built, deployed to the cloud. The engineers who built the features were the first ones who deployed it into the cloud. They were the first ones who got called when we found bugs and they had to fix it and redeploy. And this has fundamentally changed the way we build software and ship software. By the time stuff ships in the box product, when people install it, most of the features have been in the cloud for about a year, which improves the quality, and it shortens the cycle for getting feedback. Now, contrast that with like what we did with SQL Server 2005. We were in the labs for, 6, 7 years writing code, and then we shipped it, and it took customers a couple of years to adopt stuff. By the time we started getting feedback from customers about what was working and what was not working, years had gone by. Engineers had moved on, they'd been promoted, and the cycles were just really too long. And now it's much, much shorter. So this is what gives us the speed and the agility to build features, test them, experience administering features, experience feedback from customers, and so on. And there are some features in Azure SQL Database which are unique to the cloud. So they don't cross over to the box. And then there are some features in SQL Server which are unique to the on-premises product, which are not in Azure SQL Database. But most of the core engine features are all built in Azure SQL DB. So right now, for example, Azure SQL DB already has the optimizer, which is going to be in the next version of SQL Server, which is going to ship sometime later this year. So that's just an example. All right. Now, this session is about modernizing. So then the first question is, why do I have to modernize? I have SQL Server 2005. I do select, insert, update, delete, and it works. The apps are fine. Why do I need to modernize? So I'd like to spend some time just talking about that. So people have been keeping records for a very long time, mostly related to money, of course. 1700 BC, when people figured out how to do interest accounts, banks used to keep these little record books. And then Bank of America was the first to figure out how to do electronic records for banks. And that was just, in the 60s. It wasn't that long ago. Well, for some of us, it wasn't that long ago. So finance has been a big driver in taking record keeping and computerizing it. Now, whoops. Hey. I think somebody's messing with my... All right. Boy, that was a really bad one. Okay. And before computers, people kept records of everything. My grandfather was a truck driver, and he kept records of his fuel consumption, all of his routes, how much cargo he had. And the man was able to always calculate how much fuel he was going to need, depending where the destination was and what the cargo was and how much the cargo weighed. And he did it based on these paper records that he kept from his previous trips. So something as simple as that to complex financial stuff. And basically, databases have been behind modernization of these record keeping, right? Again, started from finance. You had records. Once the records were in the database, then people say, hey, we could build cool applications, that we could do not just the record keeping part, but started to introduce BI workloads. ability to look back in the history, start analyzing the data and understanding the past to help people make better decisions going forward. And over the last 2, 3, 4 decades, pretty much every industry has gone through this transition of we're going to do record keeping, and the record keeping is going to be electronic, and we're going to bring computers, and we're going to build databases. And again, it started finance, and it's probably safe to say was followed by retail because, inventory systems and such. And probably the last industry to go there was healthcare. They're probably still working on it in some areas of trying to get electronic records for healthcare. So the trouble is, though, today, in this day and age, it's not just about the records in the database. It's not just about bank accounts and credits and so on. There's so much more data that is being collected. So people are trying to figure out how to govern the data, how to ingest, how to analyze. And the data isn't just the simple rows and columns anymore. Now we have social data, we have big data, and we've moved from take every piece of data you have and stuff it in a relational database to maybe relational databases aren't the right tool for every possible data type. So I don't know, 20 years ago, you wanted to build an app and you wanted to store videos. You go, put it in a database. You wanted to store invoices, put it in a database. You want to store pictures, put it in a database. Whereas today, nobody does that. People put records that require transactional and query processing in databases. Nobody's trying to figure out how to take a 4 gigabyte video and shred it and put it in a relational database, because why would you do that? You don't do transactions on it. You don't do queries on it. So the data space has expanded. You got Hadoop. Most enterprises now have some big data systems. And the role of the database for us is still critical. There's still a lot of important information in the database. So databases now have to play in a much bigger data environment. If you have a database that cannot talk to Hadoop, or if you have data which is locked in the database and it can't interact with other data types, your ability to build application becomes very limited. So from a SQL Server perspective, our goal is to enable people to go build applications which are not just purely relational database and rows and columns. And we'll have some examples of that in the work we've done to get there. So we need more than just record keeping in the database. Again, if you just want to do simple record keeping, probably SQL Server 2005 is perfectly fine. Right? You could do select, insert, update. But you're going to have to need a lot more to build modern applications. And so where are we going with this? So for SQL 16, we basically introduced this notion of advanced analytics so that you can build intelligent applications. Now, the whole concept of intelligent application is, well, it requires a little bit of an explanation. So as I mentioned, my grandfather, truck driver, kept records of all of his fuel and distance and cargo. But it was him that calculated and did the intelligent part. The records just provided the data, and he was the one who had to figure out, well, if I'm going from point A to point B, and I have X number of tons of cargo, and this is a particularly, uphill drive, and how much fuel am I going to need, and based on matching some historical records, right? That intelligent part of looking at the records and extracting the intelligence necessary for him to figure out how much do I have to price this trip, and how much fuel am I going to need, and how much profit am I going to make, and take into consideration the weather and everything else. That intelligence came from the human mind, not from the record in the paper. The same thing is true. The records in the database don't provide the intelligence necessary for people to make good decisions. They just provide the background information. And data warehousing and BI system, took us one step further, allowing you to do historical queries and so on to use the past. But they're still not providing the intelligence you need to do predictive work. So for us, an intelligent application allows you to not just do retrospective on the data, but also predictive. And this is where we say you have the data, and then you apply some analytic algorithms to the data in order to arrive to an intelligent answer. I'll give you another example. Ski resorts, they keep track of all of their rentals and so on, right? But how many rentals you're going to need on a given weekend has a lot to do with the weather, has a lot to do with the time of the year, has a lot to do with the competitive landscape of different resorts near you, the conditions of the snow, this, that, and the other, just to come up with how many rentals you're going to have to deal with and how many people should you have on staff for any given weekend. That's predictive. And it's not just relying on the historical rental data that you might have in a database. It also has to join that data with weather information, competitive information, social information, I don't know, scraping Twitter to see how many people are planning to go to Blackcomb or Whistler or whatever, because people talk about these things, and you can extract some sentiment from that just to give you a better confidence on your predictive models. And since we're the database people and the data is a really important part of this, we need to make sure that you can build apps with SQL Server that allows you to do this kind of intelligent application building. So that's kind of gives you the background of the thinking that has gone behind SQL Server 2016 and why we talk about this advanced analytics so much and why we think that databases need to go beyond rows and columns and just queries for historical data. So what did we do recently? So SQL 16 shipped sometime in June, July of last year. We released SQL Server 2016 SP1 in November of 2016. And we did some interesting changes. We completely changed the SKU model for SQL Server. You may or may not know that there are a lot of features in SQL Server which were limited to Enterprise Edition. With SQL Server 2016 SP1, we brought all of those features to all versions of SQL, Express, Standard, and Enterprise. And the reason for this is because we have a lot of features in SQL which are programmatic features. Like if you want to use in-memory or R or column store, you have to write code. And one of the things that's happening is if those features are only available in Enterprise Edition, people tend to not write code for it because they write the code to the lowest common denominator. So with SP1, all programmable features of SQL Server are available in all versions of SQL Server. So you can actually pick up a free SQL Express and build a column store in-memory index. And we did this to allow people to build applications that leverage these features. Now, there's still significant difference between Express, Standard, and Enterprise. The operational features like always on and high availability and a lot of the online operations, the things that makes a difference between a mission-critical system and a system that, I don't know, may not be so mission critical. Those are the features which are still differentiating Express, Standard, and Enterprise, but not the programmable features. So some of the things that are in SQL, you have in-memory OLTP, which allows you to build in-memory tables, compiled stored procedures, and so on for really high throughput and low latency transactional workloads. We have column store, which is a columnar data organization for query processing. We have now enabled you to do real-time operational analytics, which means you can build column store indexes on top of your OLTP tables and be able to run queries on the transactional system without having to move data from OLTP systems to the data warehouse. And because these are in-memory structures, they don't have locking conflicts and so on. And the reason for this is a lot of people need to be able to have real-time analytics. If you want to do fraud detection and decide whether a transaction, a credit card transaction, needs to be approved or not, you're not going to run to the data warehouse, which might be 6 hours or 1 day or 2 days or 1 week old. You want to have the freshest data. So we've enabled query processing on top of transactional data. And this stuff all started with SQL Server 2012, column store came in, with 14 in-memory OLTP came in, but with 16, we've kind of put it all together. We added a lot of security features in SQL, always encrypted, that allows you to keep the data encrypted at all time. You can query encrypted data with equality joins. And we introduced Polybase, which allows you to query from SQL Server and push down queries to Hadoop system. So if you have an HDFS system, SQL can actually, you can write T-SQL that joins data from your relational tables with external data from Hadoop, and SQL will do the map, reduce, push down, run the queries on the Hadoop system, bring the results back, join, and present you with the final result of a query. And why is this important? Well, we have customers who happen to be insurance company. They collect telemetry from people's phones about their driving habits. All that data is anonymous, and it's all being collected on the internet, and it's all being stuffed in Hadoop systems. But at the end of the day, they have to do queries to actually join this data, which is in Hadoop, with the policy information, which is locked in the relational databases. And so being able to run a query that crosses both environments is very useful. And we've done a lot of work for our drivers. Now, if you like to choose a programming language which is different than what we've supported in the past, I think we're trying to support everything there is. So Java, C, C++, C#, VBNet, PHP, Node, JS, Python, Ruby, Go, Scala, anything out there. And these languages are now supported by Microsoft CSS. So if you're writing a piece of Ruby code and you're trying to connect to SQL and it's not working, you can call CSS and it will support you. Even though the SQL Ruby drivers are not from Microsoft, they're just open source code out there. And it's true for all of this stuff. I'm going to take one question, then I got to go, and then we'll have question time at the end. Yes?
Sorry. So what's the execution engine for Polybase? Are we connecting to Hive or HBase?
HBase. It's HDFS compliant.
So what's the execution engine? Is it running on Spark, or is it running on the
MapReduce? Yeah. He was asking what is the execution engine for Polybase if it's Spark, and the answer is no. We just do MapReduce pushdowns. So I have some slides, and we can chat about that later. We also just recently announced that we're going to support SQL Server on Linux. So the next version of SQL Server, which we plan to ship sometime later this year, will be SQL Server next version, whatever that number ends up being. We'll run on Linux. You can already go pick it up. We're already in the CTP process, so we just released CTP 1.2 of next version of SQL Server. The CTP cycle started last November. You can run SQL Server on Red Hat, SUSE, Ubuntu. And we also support Docker. We have Docker Linux images as well as Windows images. You can now use a Docker Linux SQL Server image to run SQL Server on a Mac. So if you like to write code on a Mac and you like to do development on a Mac and you like to have a local database on the Mac, you can just 2 commands, pick up SQL Server Docker image and have it running on a Mac. So we plan to ship this sometime next year. And I think in general, most people understand why we're trying to do this. But we want SQL Server to be everywhere. And there are a lot of private cloud stacks, a lot of enterprises that use Linux, and we want SQL to be available in those environments, so that's what we're going to do. So as a platform, this is how we look at it. The data types, it can't be just limited to the data in the database. We have to be able to reach out and access data in other systems. We're introducing data types in SQL. We support JSON now. We're putting a lot of investments in enabling developers who write code in non-Microsoft languages to be able to use SQL Server. And then platform of your choice. You want to run on Linux, Windows, it's all fine with us. And any cloud You want to run SQL Server in Azure, AWS, private cloud. Even Google supports SQL Server now. You can run SQL Server Standard, Express, and Enterprise Edition in Google IaaS Cloud. I think they're in some kind of a preview program, but it's public, so you can go try it if you want. So, as part of this modernization, you kind of need to run these mixed workloads to do intelligent stuff. So one of the things that we really are investing heavily is HTAP, which is the hybrid transactional analytic environment. And with in-memory OLTP and with column store, now you can achieve tremendous performance without impacting, right? So you can actually build non-clustered column store indices on top of OLTP tables that happen to be in memory on SQL and run queries. Stuff that was not possible with 12 or 14 or anything that came before it. This is a very popular sort of an environment for a lot of people who do, again, analytics. So fraud detection, insurance work. We have customers who are doing loan validations, where you have to be able to run queries, look at historical data. You need to be able to look at cohort information as well as do the transactions, right? So the HTAP is going to be the foundation for our intelligent app because, again, we think that to build intelligent apps, you need a lot more just than the row and the column data. And I'll give you another example of what we think is a modern thing, right? So I have a car. It's a new car. It's a 2017, car. It's a nice car. But I also live near the mountains, the Cascade Range. And this car cannot predict how far I can go. It's not as good as my grandfather, who, has been dead for 30 years now. Because when I go up the mountains, its estimate for the range keeps dropping because, of course, I'm consuming more fuel as I'm going up the mountain. And when I get to the top, all of a sudden start going down and says, now you can do 110 miles. No, you can do 120. Now you can do 150. And this is a very modern car. I mean, I just bought it. And the trouble is that the car only has access to the immediate information, like the transactional stuff, how much fuel is being consumed right this moment, and maybe some of the historical information. But it doesn't have the benefit of any more. Now, there are other cars, like Tesla, that can give you a range prediction which does not change, which is always accurate. And it says it's going to go 150 miles, it's going to go 150 miles. And the reason it can do that is because it knows where you are because it has a navigation system. It knows what road you're on. It knows what direction you're going. It knows the temperature. It knows the state of the battery, which is all very useful. But it also has the benefit of every other Tesla that has traversed that piece of road in the past, because they're continuously collecting telemetry and shipping it up and analyzing. So they can tell me that when I leave Seattle and I'm on I-90 and I'm going east, based on the amount of energy that I have, that I can go all the way to Spokane, for sure. Because thousands of Teslas have done it, and they know exactly how much energy it took to go up the mountain, go down the mountain on any different temperature. And that's a really, really smart range prediction. And the only reason it's able to do the range prediction is because it has the transactional data, what's going on right now with you. It has the cohort information from all the Teslas that have traversed this road before you. It also has the information about things like weather, right? Which is usually not in your system. Very similar to the ski resort stuff, right? Different types of data necessary to calculate and predict how far you can go. That's an intelligent app. Now, a 2017 Mercedes-Benz can't do that, and that really irks me. So I didn't buy the expensive one. Maybe that's what it is. So you got records, great. rows, columns. And most applications built in the last 20, 30 years, they said, we'll use records. Fine. An interesting thing about records is when you do transactions, you really need all the columns for that row. So transactions need the row because that's the relevant information is in the columns. But when you look at a table, and I know it's a little difficult to see with the colors, but data in tables repeats itself very frequently. Like if you have sales, retail data, like, I don't know, you sell pants. And, how many different colors of pants are there? Not very many, handful. So if you have an item description, the colored column continuously repeats. Black, 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 brown, 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 black, black, black. So when you look at data in columns, and you look at the repetition, this is when you realize why column store is an important thing, right? Because when you store data in columns, you can compress it down to almost nothing in cases where the data, like ship priority 0, right? There's 0, 1, and 2, or 3, maybe 5 numbers. So you might have 1 billion rows, but for that column, there's only 5 values you need to keep, right? So very compressible. Also, when you do queries on like transaction of, we're going to go and update Tony's salary and give him more money because he did well in this session because the evaluations were really good. You really need all of the rows. But when you're doing a query to calculate the average salary increases or whatever that has happened, you're just looking at 1 or 2 columns. So, of course, you're all database people and go, that's why you build indices, right? Yeah, so you can go build an index. But how many indices are you going to build? Build an index for every combination of a query? And some of you know how difficult that is if you want to try to optimize your schema for every possible query. When you build a column store, you basically have an index for every column. And each index is its own thing, right? So, all right. So let's do a quick demo. I have a table here. It's a line item table, and I've created several versions of the same table. This is just a basic old table. It's a heap in SQL. You got your columns, no indices. The next one is the same table, except it's created as a clustered column store index. So the entire thing is stored as a set of columns. Each column is an index all by itself, and each column is independently queryable. Then I have a table which has non-clustered column store index built on top of a regular heap. And then they have a regular B-tree index on the table. So 4 different versions of the same table. They all have the same data. And I'm going to go and query some of this. OK, so let's just look at one of them. So in this case, I'm querying the table with a B-tree index, a traditional thing which probably you have in all of your databases. It goes out there and it runs for a while. It comes back. It calculated the average discount in this table, which has several millions of rows, to be 0.05, so 5% discount. And if I go look at the resources that were used to run that query, you'll see that it used 12,000 milliseconds of CPU time, so 12.5 seconds of CPU time. And the elapsed time was 5.5 seconds. Of course, I have multiple cores in this machine, so it's running a parallel query, and this is why the elapsed time is less than the CPU time, because I use multiple CPU threads. So I'm going to run the same query for all of those 4 different tables and just see what happens when we do that. And we'll print the timing for each one and see where we end up. Now, it's going to take a few seconds to run that. But the idea is, how much CPU am I consuming to run a simple query to calculate an average from a table? All right, so here's the answer. Well, as you can see, the answer from each of the table was exactly the same, 5%. And here I print the actual times from each one of them. So a heap and no index, just a table scan, it took 16 seconds. If I built an index, a B-tree index, on that column, which is the discount column, it took 4.4 seconds. If I used a non-clustered column store index, as in not a B-tree, but a column store construct on top of the table, it took 907 milliseconds, so less than 1 second. And if I just run it against the column store table, which the entire table is stored as a column store, it only took 486 milliseconds. And the delta between the fastest and the slowest is 33 times. So this query ran 33 times faster on a column store than a regular table with a B-tree index. If I go look at the CPU consumption for this, so here you can see the one that ran on a heap used 16 and a half seconds of CPU time and an elapsed time of 16 seconds. And this one, it only took 1.5 seconds of CPU time for an elapsed time of 490 milliseconds on the last one. Why is this stuff important? Well, because if you want to run a real-time analytic system where you need to run the transactions and you want to be able to run queries, you want to be able to run these things efficiently, you want to be able to get fast responses. If you're building reporting service or dashboards, you don't want people to wait 15 seconds for the result of a query to figure out right? So you want these things to be very fast. And traditionally, people would take this data from the OLTP systems, move it to a cube or some other warehouse, do lots of indexing. And you still have to do that for some of the data that you have, some of the historical stuff. But for a lot of the real-time stuff, basically you can run it in the system. And so people say, hey, I've got 2005, it's working. Why do I need to upgrade? Because you can see 400 or 1.5 seconds of CPU time compared to 16 seconds of CPU times. That's a lot of difference in efficiency. So, why pay when you don't have to, right? Okay, so that's a quick demo. So the value of column store allows you to store the data in columns instead of the rows. You can build these structures on top of your row, so you can have fast transactions that need a row, as well as fast queries that need columns. You do a reduced I/O because you don't bring the data into memory. With the row, you have to bring the entire row and eject the columns you don't need. With column store, you just bring the columns you need. You get tremendous amount of compression because repeating data gets compressed really well. So that's kind of the column store. Okay, where can we go from here? Well, we introduced R to SQL in SQL 16. So what is R? R is the language of choice for data scientists. Now, a lot of companies now have data scientists to figure out interesting information from their data. They used to be called statisticians, but that's not very good name, I guess. So data scientist sounds a lot better. You can get a degree in data science now. And they use R for the language of modeling and predictive work. And some people use Python. And so what we've done is we've actually stuffed the R execution engine inside SQL. So you can run R scripts as part of a stored procedure. So if you want to look at a lot of data and do modeling and do predictions, like is this a good loan or a bad loan, or what is the range going to be, or is this a fraudulent transaction or not, or you look at maintenance data from an aircraft engine to figure out, when you're going to have to replace parts, will it last another 5 days or not? That kind of stuff, most of the models are written in R. Now, one of the trouble people have in their data science world is, if you want to do the interesting work, you need the data. But in order to get the data, the scientists usually don't have access to the database. So you have to get the data out of the database, give it to them so they can go analyze the data. And once they figure out how to run a model, they don't know how to operationalize it, because people are running stuff on their desks and under their desks or on their modeling servers. With R inside SQL, you can build the models and deploy them inside SQL. So the execution of the models happens inside SQL. So there's no need to move the data in and out anymore to do this predictive work. And it becomes a lot easier to operationalize because everybody knows how to operationalize a stored procedure. Now the stored procedure happens to run R. So this is the stuff where we think, okay, if you want to predict the range, you need the historical data, you might need some data externally, you might use Polybase, and you get the whole data, and then you have to run it against a model and do scoring, and you can do that inside SQL now, and you get really low latency predictive work. So what can R do for you? In your advanced analytics, you can deploy R models in the enterprises. And so one of our customers, you may not like what they're doing, but I'll tell you, it's really clever. When you go to buy an airline ticket, right, depending who you are, where you are, what time of day it is, the prices are different, right? So the prices that they come up for any given seat is predicted as to what would the market bear. So they have this really complicated software that all airlines use to basically price things, and they run based on models. And all of that data is in databases. And now they're able to push the analytics inside the database engine and be able to do this much, much faster, right? So the prices that you do don't change like once a day or twice a day. They change at the moment you're trying to purchase the ticket. Because in the old days, you knew the prices months in advance because it took months to establish prices. There were the summer prices, there were the winter prices, and then there's sales and the airlines get in fights with each other and reduce prices. And it was set X number of times a year or X number of times a month. But now every seat is priced all by itself because you can do this stuff really, really fast. Anyway, so database workloads. And this is the stuff that again, requires the database because most of this data, the transactional data you need, is in the database. It's not on Twitter or some other Hadoop system or some other big data system, right? So column store plus R scenarios. I'll just do the build. If you happen to run SQL Server transactional workload, you might have a row store for your transactions. You might have some column store built so that you can run your BI and analytics. You can run your models faster. And you can also do predictive analytics where the R scripts that need the data goes against a column store to do the query to produce the data, which is used for scoring that generates your predictive results. And so that it all runs within the context of your database. So you don't need 10 different systems, and you don't need to move the data in between systems. And not having to move the data is what makes it real time. We have a customer. They do real estate. And so, you go to these real estate sites and you look at stuff, and you search for a house and how much you're going to pay. It's really difficult because there are so many characteristics that define a house, right? Does it have a pool, not, neighborhood, schools? There's a lot of columns, and they all have to be searchable. And some of the columns are just text, descriptions and things, right? So they used to use relational tables with indexes. And it's a nightmare making sure all the right indexes are there all the time. And when you do updates, that all these indexes have to be updated. And then they also use full text index because they have to index all of the free text for description searches, right? They use spatial types in SQL, geometry, because houses have locations. So if you say, I want a house within a 5-mile radius of this location, right? You have to find it. So you have to do a spatial query to find all the houses in that 5-mile radius. So they have to have spatial indexes. They also have non-clustered column store indices so that they can get rid of their B-tree indexes so that you can query each of the columns independently. Oops. So they use every kind of storage technologies in SQL because what they're really trying to get to is that 95% of the queries run less than 5 seconds now. And the maintenance of this database is significantly easier. And each of the data types is being indexed appropriately for what it is as opposed to, right, not. So this is a lot of work that we've done so you can build intelligent apps. There's a lot of the work that's been done so that you could use some of these features to do things really fast or to do things faster than was ever possible. Some of the things went from infinitely slow to possible to do. And this is what gives us a lot of good performance badges for SQL 16. Best data warehouse performance, OLTP performance, improvements in most of the workloads. Like this geospatial stuff, it's about 200 times faster in SQL now because of the optimizations that we've done in 16. And plus modeling and scoring, which is new. A lot of benchmarks. Slides are available. You can go look at these things later, so I'll just quickly go over. So how did we get here? So set aside all of the features. Say, I don't need scoring, I don't need R, I don't need query. I just need a fast, regular old database. Great. We've done a lot of work just to make the core engine faster. Scalability, partitioning, and parallelism. And we're not talking about data partitioning, we're talking about SQL internals being partitioned. Faster I/O networks. And one of the interesting things happens these days is you might have an app that's running fine, SQL Server 2005, but it's running on an old machine and you have to go buy a new machine. Well, you can't find a machine that has 2 sockets and 4 CPU cores anymore. Like you get a machine and they've gone with 50 cores or 44 cores or 64 cores. Machines that are being built today that didn't exist in 2005 or 2003 when we built SQL. So some of the characteristics of the new machine is just not working well with some of the old databases. So if you're running really, really old software which doesn't understand the NUMA and the threads and the core density of the modern computers that you can buy from HP, Dell, and whoever, right, usually pay a severe performance penalty. So in SQL 16, we've done a lot of work to make sure that this stuff runs really fast. So I'll just pause here for a few seconds so you can take a look. Now in SQL 16, we manage all of the NUMA infrastructure automatically, regardless of the size of the machine, whether it's old or new, whether it has lots of cores or not. We do a lot of dynamic memory management to ensure that you don't run into contention in your database. We've done a lot of work to make the administrative functions like DBCC and stuff faster. We've done a lot of work in TempDB. Everybody hates TempDB. Nobody likes managing TempDB. Nobody likes configuring TempDB. And you know who else hates that stuff? Is the engineers who wrote that code. And it turns out they now have to manage Azure SQL DB, and the number of times they're woken up 2 o'clock or 3 o'clock in the morning because something goes berserk with TempDB is really high. So they've gone in there and revamped a lot of that so that they don't get woken up 4 o'clock in the morning. Now, you wish that they did this before when they were inflicting the pain on the millions of customers, but they didn't, so we inflicted the pain on them to make sure that they fix this stuff. A lot of improvements in the I/O path. As I mentioned, spatial stuff has been all rewritten to be faster. And then always on has had a lot of improvements. So if you don't use any of the new SQL stuff, and if you just use SQL, just the old stuff, it still runs faster. And in fact, there's a recording of this guy who works in our engineering team. It's called SQL 16 Just Runs Faster. So if you search for it, you'll get all of the details. So here's some examples of that. So dynamic memory object. When you run contention in your database and you see that concurrency and locking is not allowing you to consume all of the CPU because things are waiting, it's usually because some kind of an internal structure inside SQL. Is there a contention on it? And it's usually related to memory. So what we do now is we dynamically partition. If you partition the internal memory and locking structure of SQL too wide, and you don't have a very parallel system, you're just paying the penalty of this all the time. If you don't, and you run it on a very high throughput parallel system, then you run into contention. So what we do now is we dynamically manage this. And what we do is you run a system and everything is fine, and we try to keep the locks and everything to the minimum level of parallelism necessary so we don't burn a lot of overhead. But as soon as we encounter contention, we start partitioning locks, we start partitioning memory grants, and we dynamically try to adjust for the system and the level of throughput that it's running. And so you can see that as the throughput, the green line goes up, the contention goes up, and at some point SQL says, I got to partition these locks by core or by CPU or by node to remove the contention, and boom, the contention is removed, and you can push the throughput higher. So this is an example of work that we've done in SQL to just improve the memory allocation. And this stuff is really important because it consumes a lot of CPU, and we rather leave the CPU for your workloads as opposed to spinning on stuff. If you run any kind of an always-on setup, we've done a lot of work to improve the performance. In the old days, everything used to be disks and spinning disks, so you really didn't have to worry because disks are really slow and code was always faster. But as you buy modern machines, there are no spinning disks. Everything is SSD or Fusion I/O or all memory-based. So the code inside SQL that used to think, OK, I have at least a millisecond or two because I'm doing an I/O, that stuff is all gone, right? You can get to memory in microseconds. It's starting to move to the nanoseconds. So if you add always on, where you have to replicate things across and so on, you don't have a lot of margin for inefficiencies. So our goal was to say, if you run a single SQL server without any always on, without any replication, without any HADR, like you run at 100% efficiency, we wanted you to be able to run at 95% efficiency while replicating. And I think we achieved that, and we got to into doing this, we had to go reduce the number of threads, improve communication path, improve our compression, improve our encryption, parallel redo logs. The entire stack in SQL had to be improved for us to be able to keep up with some of the newer hardware. And the result is this. So we have a system, and we go and push it transactionally really hard. And the blue line is if there's a single SQL server and it doesn't have to replicate, doesn't have to wait for the network, it doesn't have to do transactions and harden transaction on a remote system. So that obviously runs as fast as possible. And it's doing about 292 megabytes a second at 99% CPU utilization. So that's the best. This is, if you add a single replica using SQL Server 2014, is the yellow line. So your 292 megabytes a second throughput drops down to 88 because of, replication and moving data and remote systems and so on. The red line is SQL Server 2016 without encryption. And the white line is with encryption. And so achieving a 91 and 94% efficiency, which is reasonably close to our target. So it basically allows really, really high throughput transactional systems that really depend on low latencies to have HA and replication without paying a performance penalty. Well, without paying as much of a performance penalty as it used to be. Now, you can say, hey, Tony, that yellow line for SQL Server 2014 really sucks. How come you guys did so badly? Well, back then, we didn't have some of the encryption and compression stuff that exists in modern computers. And so we've done a lot of improvements that pushes down a lot of work to the processor as opposed to running in code. So some improvements in always on. And again, if you search for SQL Server 2016 runs faster, you will find there's a really detailed description of all of the items that went into 16 performance improvements, without even looking at some of the newer functionality. All right. So the largest machine we've run SQL on is the HP Superdome 640 cores and 24 terabytes of memory. So if you have really large workloads, we run and we scale. I don't know what you would do with a system this big. There aren't very many applications or workloads that require stuff like this. But the point is, we do the improvements necessary for the software to scale, right? Even on a 640 core machine with 24 terabytes of memory. And the improvements you have to do for things to scale here means when you're running on smaller machines, you're just even more efficient. All right. Now, I did mention that the same team that does SQL Server also works on Azure SQL Database. But what we do for Azure SQL Database is very different than SQL Server as far as engineering goes. The database engine is the same. So any improvements you put in SQL Server, SQL DB, it's all the same. Like all of the replication improvements we did for Always On, it's being used by Azure SQL DB every day because all databases are replicated. All of the memory improvements are there. All of the improvements are, it all starts in Azure SQL Database and then ends up in the server. But when we're working on the service, most of the engineering work goes to improving the service element, not necessarily database core functionality. And what do we mean by that? Like, you can change the size of the resources your Azure SQL database has, like from 2 core to 8 core, without taking the database down. Right. You can go from 8 cores to half a core. You can go from a $1,000 database to a $5 database without, So this is on-the-fly scaling up and down. Learns and adapts. So in Azure SQL DB, we have all the telemetry all the time. So we can actually do threat detection. Like we can tell if somebody's database is being hacked. If somebody's doing a password brute force attack on a database, we just see it. We have a lot of anomaly detection systems that we built using, guess what? Predictive models. So we take all of the telemetry that comes from Azure SQL databases, and we run them through predictive models, and everything is baseline. So for example, if you drop a table in SQL Server, a table that doesn't exist, it generates an error saying table doesn't exist. Big deal. A lot of people do that all the time as part of their normal application thing, right? They don't check to see if the table exists or not. They just drop it and ignore the exception. Well, we measure this stuff. And we can tell that there's a database that gets about 500 errors of specific type on any given day. But if on one morning you come in and you're seeing 1 million of the same error, then there's something wrong, right? So this is what we call anomaly detection. So we'll send an email to the customer saying, hey, you probably deployed an app, doesn't match your schema, or you changed your schema and forgot to change the app, and you're getting lots of errors. Or we can detect exfiltration. Like we see a query that's coming from a place we've never seen before for a given app running on a given database, and the query is running a pattern which is unknown to us, we've never seen, and all of a sudden a transactional system is seeing megabytes or gigabytes of query. Well, that starts to smell like maybe an exfiltration. Like somebody hacked in and is downloading data from this database, right? So we generate an alert, send it to the customer with the log records, with the audit records, saying this query ran at this time from this place. You should check it out. Maybe somebody's trying to extract data from your database. That's the stuff that we invest for SQL DB. So it's about anomaly detection, performance insight, index advisor. Like, we're database people. We know what the optimizer is doing at all time, and we can always tell that there's a query that runs that doesn't use an index and is doing full table scans. And that query would benefit if there was an index. So we pop a little notice in your portal saying, hey, maybe you should build this index. So it's called an index advisor. And you can take the advice or not. You can dismiss the advice. You can tell us to automatically create indexes that we think will improve your performance, and we'll do that for you. Or maybe there are indexes that are never used, and we recommend that you drop them because they're never used, and they're just an overhead. And we try to make sure that all of the stuff that we give you is actionable, right? So this is what we do with a service, because Azure SQL Database is a database It's a cloud database service. So the cloud and service elements are very, very important. And what is a good service element? Like, we noticed that you have a database and you're paying us $1,000 a month, but you're using 5% of the resources that you're paying for. We will notify you saying, hey, maybe you should downgrade to a cheaper database, right? So there's a lot of recommendations and insight that we give you when you use Azure SQL Database. And that's the kind of investments that goes in there. We also take advantage of the fact that we have some visibility over like what is the optimizer doing across millions of databases, and that improvements that we put in there ultimately comes into the SQL Server product. So we've made a lot of improvements in SQL Server, next version of SQL Server, which will ship in 2017, based on telemetry that we collect. Like a lot of stupid things that the optimizer does, right? Now we have the benefit of millions of databases and billions of queries and go, maybe we shouldn't do that. Some assumptions that may have been wrong 3 years ago when somebody wrote a piece of code. So it's a very mutually beneficial sort of a system. As I said, you can scale up and down. We have a concept of pools. Like you can put databases in a resource pool where they share. Like if you have lots of unevenly used databases, they can share resources. They can be individually governed, but they can spike. You can move stuff in and out. And then there's a lot of components that are shared between SQL DB and SQL Server. Again, because it's the same engine. Occasionally, we lie about the version numbers so we don't break tools. So occasionally, Azure SQL Database will tell you that it's SQL Server 2016 when it's really 17, right? So we manage a lot of the versioning, so things just work. So things like operational analytics, like this mix of OLTP and column store and queries, it works in SQL DB the same way as it does in SQL Server because it's just the same engine. Let's see. The security stuff is all the same. So always encrypted, dynamic data masking, TDE, auditing, all of the security infrastructure. SQL Server, by the way, is the database known to have the lowest security incidents for the last 6 years compared to its peers every year for the last 6 years, compared to Oracle, DB2, MySQL, and HANA. So we're trying to keep the thing as secure as possible. So something like Always Encrypted, which was introduced in SQL DB and SQL Server 2016. Imagine you have some piece of data in the database that you don't want anybody to see, ever, including the DBAs. Let's say this is a credit card number. Everybody stores a credit card number as a string. Nobody does transactions on a credit card number. Like there's not an application that says credit card number plus 7. What people do with credit card numbers is they put it in a database and they get it from the database. So from a transactional perspective, it has very low requirements. There's really no reason for that data to be in plain text in the database. Now, when you go to your doctor and you check in, the first thing they want is Social Security number and, I don't know, credit card. So the person who's taking these things, they already have it. They don't need to go crack into a database to steal it because the nurse has the credit card number and the Social Security number, right? And that's what we call a secure point of use. So that's the only place the thing needs to be seen. And when you query, like you come in and go, here's my Social Security number, they look up your record. You just gave them the Social Security number. They don't need to steal it. You just gave it to them. What they need to do is query the database and bring your records back. So with Always Encrypted, what you can do is secure the point of use with the SQL client, where the encryption happens at the client side, and it's completely transparent to the engine. So what happens is you put in a query, select name from patients, where Social Security number, some number. As that goes through the SQL client drivers, the data is encrypted. The client driver gets a certificate or a key from a key management system independently, and it has access to the key where the database engine does not. So the database engine cannot decrypt, but the client can. By the time the data, that query, arrives at the database engine, that social security number is encrypted using the same key as before. And the data in the database is also encrypted. So when you do equality joins, you can see that that thing matches that thing. You don't even know it's a social security number. It's just a string now. And as the data is returned, it's decrypted at the secure point, and it shows up as clear text. And so this allows you to take some specific pieces of data like social security number and credit card number and encrypt it. So if somebody hacks into the database and take the entire database, or they run a query, all they get is gibberish, because only the client that has access to the hardware key management system can actually encrypt and decrypt. So you can use this on-prem, you can use it in the cloud, you can use this in environments where the operations that's managing the database is not trusted in the same way as the users of the application. Again, in the case of the nurse, they already have the social security number and they already know what it is. The DBA has no reason to know your social security number ever. So this is the kind of technology that we've been working on because security is very important to everyone, and this is the kind of stuff that we can actually build in Azure SQL DB, try it, get feedback, iterate on it quickly. So by the time it ships in the box, it's actually a usable feature. In the old days, something like this would show up, and then you'd have to wait for the next version of SQL before it was usable because it would take that long for us to get feedback on stuff like this. We've done a lot of work for data warehousing in SQL. So obviously, any of the work that we've done for the analytics stuff shows up in the column store. Those are all benefits for data warehousing. So something like Azure SQL Data Warehouse, I mean, it only stores column store, right? It doesn't use row store at all. And most data warehouses don't use row store anymore. So a lot of work done for performance. And as I mentioned with Polybase, we now support the ability to create an external table. An external table is a SQL, T-SQL construct. You run T-SQL, create table, and you have the keyword external. You define a table, and then it points to an HDFS endpoint. And then you can run T-SQL that joins the data, right? And so you don't have to move the data from the database to your Hadoop system because you want to do a join between data in Hadoop and SQL. And you don't have to move the data from Hadoop into the database because you want to do that. Now, there's some type of data that it would defeat the purpose of using Hadoop if you had to move the data to SQL. This is a very common scenario for IoT. You know, all these devices that are collecting telemetry from millions of devices out there, all of that stuff ends up in Hadoop. All of that stuff is data you don't really know how you're going to use someday, and you store everything, right? Really not a fit. But when you do figure out and when you want to run queries against it, you want that stuff to be queryable. So that is the concept of running T-SQL with your relational system. If you search for Polybase, you will get the detail of all the versions of the Hadoop that we support, Hortonworks and so on, and the versions of the specific ones. And with SQL Server Enterprise Edition, this could also be parallelized. So you can have distributed processing with multiple SQL nodes that hit the Hadoop system. So if you have a very large system, you can actually do parallel processing. So it's not limited to just a single SQL engine. And then end-to-end mobile BI, in SQL 16, we updated SSRS, SSAS, and we added all of the mobile reporting. It's all HTML-based. The Silverlight stuff is gone. Now you can actually get really beautiful graphs. We have a lot of people who are just upgrading just to get to the new version of SSRS. It also runs on all mobile devices. So you can have a SQL Server reporting service, and you can connect to it with the Power BI app on your iPhone and see reports. It's really beautiful. And then upgrade easily. We've done a lot of work to make upgrades easier because we do upgrades all the time for Azure SQL DB. And so backwards compatibility and breaking changes and such is very painful. So we spend a lot of time making sure upgrades are easier. And one of the things we've introduced is Query Data Store. I don't know if you've had any experience with Query Data Store. Anyone? So Query Data Store is kind of like your flight data recorder for the database. It basically keeps track of all of the query execution statistics, plans, and everything. And every once in a while you come in and everybody says some app is really slow, and then you have to go figure out why is it slow and what happened and so on and so forth. It takes a lot of time to investigate these things. With Query Data Store, you can walk to the database and say, show me the top 10 CPU consumers. And then show me the top 10 query consumers in their historical trend and which one of them has changed. And you see, oh, this query used to be number 914 with resource consumption. It's number 1 today, right? And then you go and you see that the plan has changed because you do compare of the plan. And then you see, maybe somebody accidentally dropped an index because it's not using the index anymore, for example. So you could do a lot of investigative work with Query Data Store because you get the historical trends, and it's really easy to drill down. But the other thing you can do is, going forward, you can upgrade to SQL 16, but set the compat version to 14 or 12, and then run Query Store, and it'll collect all of your query stuff. And then you change the compat, which is just alter database compat to SQL 16 compat level, and run your workload. And then you can compare in Query Store the difference between SQL 16 optimizer and SQL 14 optimizer. And if there's no difference, then you can easily upgrade. If there's a difference, then you know what the difference is and what it would take to fix it. So you don't have to be blind about these upgrades anymore. So again, we built the Query Store initially for our support organization because they needed to quickly diagnose things. But it's been a very popular thing with customers, and so we've expanded on it a lot. So this is the stuff in SQL, and this is the technologies we're working on. It's all the same stuff in SQL Server and Azure SQL Database. The core engine is the same. The features are the same. And you can get it anywhere you like. And as we go forward with SQL vNext, you can get it on Linux and other environments. So I'll pause here, and I'll take a few questions. We're running a little late, but take a couple of questions. Yes? Yes.
With this whole in-memory column store, do you see we take queues or we can directly execute query on 12 APIs?
Yeah.
So
So what we've seen is that there are workloads that will continue to use cubes, and there are workloads that will continue to use those models. But one of the things we've introduced in SSAS is a data-less model, where you can still have a cube model, but instead of moving the data to SSAS, you can actually run dynamic queries. Because if you can get the database to respond to the queries fast enough, then you don't have to move the data. And so we've seen people using this method, the data-less models in SSAS, and there are some people who are just using column store. But for some of the dashboarding stuff where you need sub-second responses, like your executive dashboards, still cubes are very much the way to go. So it all depends on your tolerance for the latency and the size of the data. But we think that there's a mix, and so being able to enable the mix is really the key. And the data-less SSAS models is a really useful way of going about it. One more question. Yes?
how does column store work with compression and table partition?
Same. You can partition, so it doesn't make a difference. And with compression, column store itself has a better compression. So there's no point of doing row or page compression when you're using column store. Column store has its own compression settings, including archival compression, which does really spends a lot more CPU time trying to compress. So it all works. All right, thank you very much. If you have questions, you can send it tweet, or my email address is tonypet@microsoft.com. That's just Tony Pet, like a dog, pet dog. You can't forget it, right? tonypet@microsoft.com. Thank you.